On basic differentiation, we start with the definition of the slope or the gradient of a tangent, which we know that it is equal to the gradient or slope of that curve at that particular point given. And it is defined as this limit, that is the limit of f of x plus h minus f of x all divided by h. Once again, this definition is a definition of the derivative of f of x, which is also the slope or the gradient of the curve, as well as the slope and the gradient of the tangent at that particular point of contact between the curve and the tangent. Also, we need to realize the notation that we use. We use d over dx or dx, which is capital letter D, and with the subscript x. Therefore, if we are asked to find the derivative of f of x, we also use the notation prime, which is shown in the last line as f prime of x, d over dx of f of x, dx of f of x, which is equal to that limit, which is also equal to the gradient of the tangent. The second one is a bit complex compared to the previous one. We've got 4x cubed plus 5 over x. Same story, we write down the expression for our derivative, and then thereafter substitute x plus h into the function for us to get f of x plus h. Again, minus 4x cubed plus 5 over x. Note that I've put in brackets because there are two terms to f of x, and then thereafter simplify. First things first, remove all brackets in our simplification so that we get to be able to eliminate h from the denominator. So note that when you remove the bracket from this term f of x, make sure that you multiply by the negative sign to all the terms inside that bracket. And also make the first expression, okay, the first two terms to be under one common denominator, which is x plus h, and also recognizing that the last term is 5 over x, so that means it has to be included. So all the terms that are in the numerator have a common denominator, which is x into x plus h. And then thereafter we simplify, and I took h out so that h and h may cancel out, and then we'll be able to substitute h equal to 0. Please check the simplifications, how we got rid of the cubed there. I hope you still remember the binomial theorem is also used to get those terms. The first term should be 1, the second term should be 3. I'm looking at the coefficients. The term should be 3 and the last term should be 1. So it's 1, 3, 3, 1, and then you multiply that by that 4 that was out there so that we get those first 4 terms. So please check all the steps and see whether we'll get the same answers. Then the third last step, we don't have h now in the denominator. Then we can be able to safely substitute h equal to 0 in, and simplify, and that's the expression that we got as the derivative of 4x cubed plus 5 over x. Please check all the steps to see whether you are going to get the same solutions. Number 3, we've got f of x equal to the square root of x. Now we are meeting a different kind of an expression. So first things first, in place of f of x plus h, you've got the square root of x plus h. So the numerator becomes the square root of x plus h minus the square root of x. And then we do what we call rationalization. And I'm hoping that you still remember how to do the rationalization. All you need to do is to change the sign between those two terms and divide by the same. So all in all, you're multiplying by 1. Then multiply out. Our main focus is to make sure that we get rid of h in the denominator before we substitute the value for h equal to 0. So in my expression here, I've got x plus h minus x in the numerator. So that means I'll only have h as the numerator. So h and h will cancel out, and then leaving me with an expression that I can be able to substitute the value 0 for h. And that's what I got, 1 over 2 square root of x. Please check and do those multiplications yourself. Now we move on to the chain rule. It's called the chain rule because it's the derivative of composite functions. Remember, the composite functions, it could be f of g, or it could be f of g of h of x. It could be a combination of about 4 functions as for that matter. So we have to recognize the derivative of each of the functions in that composition. So now, just as for definition purposes, we'll just use a composite of two functions. So we have here y equal to u of x. Y is a function of u and u is a function of x. How to differentiate that? We start with the outer function, which is u. So we differentiate y with respect to u and then u with respect to x. Note that we do use a multiplication of the, so we call it a chain rule because it's a chain of events. You move from outer function to the inner function and to the innermost function. So we get a product of a lot of derivatives. So let's go to examples. I'll start with the simplest one where it's the function is a power function. We've got here 1 minus 3x squared all to the power 4. So the first thing we do is to differentiate this expression with respect to the power. We have to take note of that power. So it will give us 4 into 1 minus 3x squared all to the power 3. Noting that we do recall the derivative of x to the power 4 is 4x cubed. So that's what we do. And then thereafter, multiply by the derivative of the inner function, which is 1 minus 3x squared. So the derivative of that function is negative 6x. We differentiated the power as if the inner function is just one term. Now let's go to number 2. Now we have a trig function with an exponential function as its argument. So let's start with what is the outer function. The outer function is the square, which is the power. So we start with the power, hence we get 2 sine of e to the power sine squared t multiplied by the derivative of sine now, which we know should be cos. Remember, we have to take down the argument of sine. And then we go to the derivative of the argument. So we started with the power of sine, and then with sine, and then the argument of sine. Argument of sine is an exponential function, so we know the derivative of e to the power x just gives you e to the power x. That's what we get here, e to the power sine squared t, multiplied by the derivative of the power of e, which was sine squared t, and it gives us 2 sine t, because we have to first differentiate the power. Chain rule requires us to first differentiate the outer function. So we've got 2 sine t multiplied by the derivative of sine t, which is cos t. I'm hoping that you're noticing the chain. It was sine squared, so we first start with the power of sine, so it's 2 sine. And then thereafter, the derivative of sine, then the derivative of the exponential function, and then the derivative of the power of that exponent. Let's go to number 3. Number 3, you've got tan of sine of the square root of 1 plus t cubed. We've got 3 functions there in composition. So the derivative of tan is sec squared. Note that we have to take the whole argument as it is, multiplied by the argument of tan, which is sine square root of 1 plus t cubed, and we note that we have a composition as well. So we start with the derivative of sine, which gives us cos, and the argument of that sine was the square root. And then we go to the derivative of the square root, which we know is 1 over 2 square root of 1 plus t cubed from the tables, multiplied by the derivative of the argument of the square root, which is 3t squared. I'm hoping we are together here. We go to number 4. Number 4, we've got 8 times the square root of 1 plus square root of x. So we'll have to start with the outer function first. The outer function is the bigger square root. So we've got that 8, which is the coefficient, multiplied by 1 over 2 square root of 1 plus square root of x, multiplied by the derivative of what's under the big square root. We know the derivative of 1 is 0, and the derivative of square root of x is 1 over 2 square root of x. We've got number 5, y equal to sine of cos of tan x. The derivative of sine is cos. That's where we start. Taking down the argument of sine as it is, multiplied by, we're going inside. The derivative of cos is negative sine, and the argument of that cos is tan x, so we write tan x, and then the derivative of tan x, which is sec squared x. Note that we need to recognize the argument of each term we're differentiating. Then we go to number 6, the derivative of ln of cos of 2x all to the power 3. Now, first things first, the derivative of ln of x is 1 over x. So that's where we start. So it's 1 over the argument of ln. So that's what we got here, 1 over the argument of ln. Then multiplied by the derivative of the argument. The first thing that we encounter is cos, which gives us negative sine, and the argument of cos was 2x to the power 3. So that's what we have. Multiplied by the argument of cos, which will be we start with the power, which will have 3 into 2x to the power 2, multiplied by the derivative of 2x, which is 2. Now we go to number 7. We've got ln cubed cos 2x. So now note the way I've rewritten it so that we understand that ln cubed is ln cubed of cos 2x is ln cos 2x all to the power 3. So first differentiate the power, which is 3 ln cos 2x to the power 2, multiplied by the derivative of the argument of that power, which is ln cos 2x. So we have 1 over cos 2x, and then we differentiate cos, which is negative sine 2x, multiplied by the derivative of the argument of cos, which is 2. Number 8, we've got sine squared of e to the power sine squared t. I'm hoping that we are able to do that problem based on what we've already done before. And take note of the exercises. A little bit complex, but doable. Now we go to the product rule and the quotient rule. Product rule, note that we are talking about a product of two functions. Quotient rule, we are talking about the division of two functions and not more. So for a product, f of x, g of x, when you differentiate, you start with differentiating one function multiplied by the original of the second function plus the first function times the derivative of the second. So it's f prime of x times g of x, which is the original function, plus f of x times the derivative of the second function. Note that we're using plus between those terms. Now we go to the quotient rule. Quotient rule is f of x divided by g of x. So first thing first, take the denominator up to the numerator, multiply it by the derivative of the numerator minus the numerator times the derivative of the denominator. All of this is divided by the denominator squared. First things first, denominator up times the derivative of the first of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Let's do some examples. Note that in our examples we'll have the chain rule also included, product rule as well as the chain rule, because those are the kind of problems that we encounter. So let us say we were asked to find the derivative of sine x ln sec x. So now our f prime of x will be, note that this is a product of two functions. So we start with the derivative of the first function times the original second function. So it's cos x times ln sec x plus the original first function, which is sine x, multiplied by the derivative of the second function, which you know should be 1 over sec x multiplied by the derivative of the argument of ln, which is sec x, which gives us sec x 10x. If we were asked to simplify, we would get sine x times 10x as the second term. Once again, there's a product rule. So differentiated the first function first, which is sine, and it gives us cos, and we multiply that by the second function plus the derivative of the second function multiplied by the original first function. Here, number 2, we've got now the quotient rule, ln of sine x divided by x cubed. Quotient rule requires that we take the denominator up, so it's x cubed multiplied by the derivative of the numerator, which is 1 over sine, because that's what we have as the derivative of ln, 1 over sine x multiplied by cos x, which is the derivative of the argument of ln, minus the original numerator, which is ln sine x, multiplied by the derivative of the denominator, which is 3x cubed. Remember that we always subtract. You differentiate the numerator first minus the derivative of the denominator. When you are going to differentiate the denominator, there must be that minus sign. All of this is divided by the denominator squared. If you are asked to simplify, then cos over sine, you'd be able to say it's quad x. Okay, we go to number 3. Quotient rule is in the argument of the last term. All the other terms, they use the chain rule. Now let's do this. The derivative of the square root of sine cubed of the cube root of x. First thing, chain rule requires that we move from outer to inner. We first differentiate the square root sign, which is 1 over 2 square root of that whole argument, multiplied by, we go in under the square root sign. We first thing that we get is the power of sine, which is the cube. So that means it will give us 3 sine squared of the argument of sine cubed, multiplied by the derivative of sine, which is cos, multiplied by the derivative of the argument of sine, which gives us that term. Please, I need you to check the derivative of the cube root of x, whether I got it right. Then we go to the second term, plus. Once again, we differentiate the power, which is 2 cos of the square root of 1 minus x squared, multiplied by the derivative of cos, which is negative sine of the argument of cos, multiplied by the derivative of the argument of cos, which gives us negative 2x divided by 2 square root of 1 minus x squared. Then we go to the last term, cosec squared of x over x plus 1. Power first, which gives us 2 cosec of that argument minus the derivative of cosec, which is negative cosec cot. Note that each of those trig functions must carry the argument of the original function multiplied by the derivative of the argument, which is the quotient rule used. Then we have x plus 1 into 1 minus x into 1 all divided by x plus 1 all squared. Remember, quotient rule requires that you take the denominator up, multiply it by the derivative of the numerator, minus the numerator times the derivative of the denominator, and divide all those terms by the denominator squared. Number 4, we have a product of two functions, so we'll use the product rule. And note that the first term is a composite function. So first start with the power. So I've got 5 into 3x plus 7 all to the power 4, multiplied by the derivative of 3x plus 7, which is 3, multiplied by the second function, which is sine 2x. So we differentiated the first function and we take down the second function as it is, plus the first function times the derivative of the second, which is cos of 2x, multiplied by the derivative of 2x, which is 2. Then number 5, we have a quotient rule. So denominator up first, multiplied by the derivative of the numerator, which is cos of 2x plus x squared, plus 2 plus 2x, which is the derivative of 2x plus x squared, minus the numerator as it is, times the derivative of the denominator, which again is 7 into 5 minus x to the power 4 to power all to power 6, multiplied by the derivative of 5 minus x to the power 4, which is negative 4x cubed. All of this is divided by the denominator squared. Now I'd like you to do number 6 and number 7, making use of the appropriate rule, whether quotient rule, product rule, or the chain rule. We go straight to implicit functions. When a function cannot be explicitly written as y equal to a function of x, then we say it's implicit. That is why we say when a variable y cannot be explicitly isolated or algebraically isolated, then we say we have an implicit function. So how then do we find the derivative of y with respect to x for implicit functions? The first thing we notice is that y is a function of x. So it means we'll have to have a chain rule. And also when we have a term that has got both x and y, then we have to use the product rule. Hence, the first step is to differentiate each term of the given expression and then use product rule for all the terms that have got both x and y. Second step, you rearrange and make dy over dx the subject. Let's quickly go to examples. We've got 3y to the power 4 plus xy squared plus 2x cubed minus 6 equal to 0. So differentiate each term remember, when a term has got y, it means y is a function of x, so the chain rule must apply. So the derivative of 3y to the power 4 would be 12y to the power 3. That is correct. Multiplied by the derivative of y with respect to x, because y is a function of x. It's the same as what we said, that y is equal to u of x. So we differentiate y with respect to u and then u with respect to x. That's what we're doing here. And then the derivative of x y squared, product rule, because y is a function of x as well. So product rule, differentiate x first. That gives us y squared, which is 1 times y squared basically, plus x times the derivative of y squared, which is 2y times dy over dx, plus the derivative of 2x cubed, which is 6x squared, equal to the derivative of 0, which is equal to 0. So we start with the first thing, differentiate each term with respect to x. Then we'll rearrange and make dy over dx the subject. So all the terms that do not have dy over dx go to the right hand side. In this case, we got negative y squared and minus 6x squared. And then we take out dy over dx as the common term, and then make dy over dx the subject. Let's do some more examples. We've got 2x cubed y plus y squared plus x all to the power 3 equal to x to the power 4. Differentiate each term. That's the first thing we do. So we've got here 6x squared y, which is the derivative of x cubed, which is 3x squared. So we know that we're going to use the product rule for the first term because there is a combination of x and y. So we have the 6x squared y. We take down y as it is, plus 2x cubed as it is, times the derivative of y with respect to x, which is just dy over dx, plus second term, composite function. So we start with the power. We'll get 3 into y squared plus x all to the power 2 multiplied by, now we go inside, we'll have 2y times dy over dx. Please remember, all the time when differentiate y, we always multiply by the derivative of y with respect to x. And then the derivative of x, which is 1. All of this equal to the derivative of x to the power 4, which is 4x cubed. Rearrange all the terms and make dy over dx the subject. So please check my use of brackets, check my signs, and see whether there are no mistakes. Number 3, we've got cot 2x minus 3 cosec xy equal to y squared. So now for cot 2x, the derivative of cot is negative cosec squared 2x. But we have to multiply it by the derivative of the argument, which is we're getting 2, minus, now we go to the second term. We've got minus 3 into the derivative of cosec is negative cosec cot, multiplied by the derivative of the argument of cosec, and we know that we use the product rule. Please keep this in mind. The derivative of xy will always give you y plus x dy over dx. Right hand side, we've got 2y times dy over dx. Then we make the rearrangements. All terms that do not have dy over dx to the right hand side, all the ones that have got dy over dx to the left, and then make dy over dx the subject. Please check to see whether this answer is the correct one. Number 4, we've got y equal to x minus ln squared of x plus y. Derivative 1 minus, note that chain rule applies. We've got 2 ln x plus y multiplied by the derivative of x plus y, which is 1 plus y prime. Then you make y prime the subject. Please check whether everything works out. Here are some exercises that you can work with and look for any other exercises where the implicit differentiation is applicable. We move on to logarithmic differentiation. Note that when we've got complex expressions that have products, quotients, and powers, and we're supposed to differentiate it, we can simplify it by introducing logs on both sides of the equation. Simplify by using the applicable laws of logs, and then thereafter find the derivative of each term and then isolate y prime. Note that in the final answer, your answer, if it has got y, substitute y with the original expression that was given to you for y. And we call this whole thing the log or logarithmic differentiation. Now we go to examples on log differentiation. Number 1, the expression of y has been given to us, and we're supposed to find dy over dx. So to simplify the expression, we introduce logs to both sides. So in this case, we use ln, which is easier to differentiate. Then we use the laws of logs, which are also applicable to the natural log. Please check whether we used the laws of logs appropriately for the right-hand side. And then next step, differentiate. The derivative of ln y is 1 over y times the derivative of y with respect to x. Please check whether the other 3 terms have been differentiated appropriately. Now I need you to look at the second last step. We end up with y times the expression that we got on the right hand side. And we already have an expression for y. So in place of y, we substitute the original expression without simplifying it. Substitute the original function to give you the very last answer. Please check the differentiation. Please check the use of the chain rule and also the simplification. Number 2, once again, the expression given to us is a little bit complex, so we introduce ln on both sides and then do the simplification. So once again, cot cubed is 3. The ln of cot cubed is 3 ln cot x, and then we've got ln of 10 x squared. Note that x squared is the argument of 10, so that power cannot be removed and made the coefficient. And then the power of 3x squared plus 1 can be made the coefficient. Then we find the derivatives. Please check whether we've used the derivatives appropriately and the chain rule appropriately, and as well as the simplification. So for y prime, that's the expression I got, and then I remembered in place of y, I have to substitute the original expression that was given for y. Please check each and every step to see whether you will get the same answers. Here are some exercises. Making use of log differentiation has been specified to determine y prime. Note that you can use y prime or dy over dx interchangeably. Number one, note that we don't need to introduce ln because already ln is there on the right hand side. All you need to do is to simplify the right hand side and then differentiate both sides. For the others, we need the introduction of ln on both sides. Again, the last 5 exercises make use of log differentiation to simplify as well as find y prime. Please do this, challenge yourself, and see whether you'll get everything right.